Yeah. So we'll start with another exciting session. So the first talk of this session is the crowdfunding game by Moran.
Yes, very, very convenient, all this. Okay, so hello everybody. I'm going to present a work titled The Crowdfunding Game. It is a work I've been working on with Itai, Arieli, and Rann Smorodinsky. So before I start, a couple of words about crowdfunding. Oh, okay. So crowdfunding it was the main buzzword before blockchain and everything. It was the buzzword a couple of startups like to use a couple of months ago, which is basically a $53 billion industry in 2015. You can see some of the most successful projects out there, which is the DAOs, the Pebble Time, which introduced the smartwatches, the Ubuntu platform, which afterwards was less successful, the Ubuntu for Edge. Anyway, we wanted to study this mechanism, this scheme, this new fundraising scheme where an entrepreneur comes to a lot of different individuals to ask for money. So first we noticed that people use crowdfunding for one of two goals. It's either that I have a product that I want to produce, and I'm raising some sort of initial funds as a proof of concept to take to traditional investors and get more money for my product. Usually when I have just a concept of an idea or a cool video or something like this. The second purpose is to gauge the market demand for an unknown product. For instance, I want to produce the fidget cube, and I don't know if the fidget cube was one of the, look it up. Fidget cube is a small cube with all sorts of buttons you play with. So, and I want to see if people want to buy this product, so I'm pre-selling them. And if I am able to raise the fund, then I am able to produce the product. So these are the two main reasons we'll keep in the back of our hand. How does a crowdfunding campaign looks? Usually a guy wanting to present a product that he doesn't know, that you don't know anything about, like, do you want vegan meals? Sorry, all the vegans in the room. He sets some sort of goal, offers a menu of prices, and people can choose whether they commit a contribution beforehand or not. And if they commit, and if the total sum of contributions surpasses the goal declared by the entrepreneur, then the product will be launched and everybody will be happy or not happy. And with vegan meals, they'll be happy, of course. While the majority of literature focused on this guy and how to set the mechanism correctly, we are more interested in these guys, on the contribution and the people who made the contributions. We want to see, basically, if I have a product of unknown quality, how well can I be sure that the product that went through the crowdfunding process is in fact good. And how do we do it? We do it with a model. We present a new game called the crowdfunding game. As we'll see in the end, it has other uses as well, where basically it is a game played between n players, and you have some sort of threshold that is set in the background, but we take the threshold as a given, as one of the parameters, where you have a product that can be either of high quality or of low quality. There are n players. Each player can either commit a contribution or join or opt out, resulting in zero utility. Now, the utility in this presentation is normalized. We say that the utility of the object to the consumer is 1 if he signed up and if the total number of people who joined in is greater than the threshold, greater or equal to the threshold, and if the state of the world is good. On the other hand, if the campaign succeeded, he joined in, and the state of the world is bad, then the utility will be -1. The results hold for other utility functions, but the main idea is that you have two valuations, you can think about it as a product that is worth either 2 or 0, and the price is fixed to to 1, and you get this utility function. So this is, like I said, this is a asymmetric information game where the state of the world is unknown. We assume there is some sort of probability, which, again, for this talk, I'll normalize to half, that the world is in fact good. Every consumer receives one of two signals, either high signal or low signal, and the probability that the signal is correct is given and is greater than half. We mean that the signal is on average correct. I mean, if everybody would just tell their type or act upon their type, we would know if the product is good or bad, in a probability, of course. Okay, so some definitions. We are looking at mixed strategies, and we are looking at Bayesian equilibrium of the game, where the behavior of the players is determined solely by their type, a symmetric equilibrium. Now, the problem with using just a symmetric equilibrium, as mentioned here, is that as long as you need more than one guy to, as long as B is greater than 1, you basically have the equilibrium where nobody participates. If nobody participates, then I'm indifferent between participating or not participating. My utility is 0 in either way. So we narrow the definition only to non-trivial equilibriums. Non-trivial equilibriums are equilibriums in which there is a positive probability that the product will actually be manufactured. Now, the first result we are going to present is that in this type of games, you only have a single equilibrium.
So this is a simultaneous game?
Yes, yes, this is simultaneous. We're trying now to, it's a static simultaneous game. We are actually working on extending it to dynamic settings now. So the only equilibrium in this game is one where if I receive the high signal, then I will surely commit. And if I receive the low signal, then I will assign some positive probability for committing. Now, this seems a little counterintuitive, because if I received a bad signal, why should I commit? More on that next slide. So in order to gain some traction to the model, let's go through a very simple example. I'm setting P at 3/4, and let's see what happens when the threshold is 1, and there are only 3 players in the game. So in this case, it's enough. My action is, it's not only commitment. Actually, if player I decides to contribute, this means that the number of people who join is greater or equal. Of course, there is a mistake, greater or equal to 1, no matter what the other players do, which means that the product will be manufactured. But still, so in this case, I know that if I receive the low signal, then with probability 1 minus P, the state of the world is good. My signal was wrong. And with the probability P, my signal was correct, and the state of the world is bad. The product is bad, which gives me a negative utility no matter what the other players do, and therefore my dominant strategy is to opt out. Similar calculation shows that if my state of the world is high, then I always opt out. And then I never opt out, sorry. So the only equilibrium here is an equilibrium where the only contributors are people with high signals, and the people with low signals don't contribute, which means basically that people play according to their signal. People are truthful, which seems kind of cool. So we want to know if this is always the case. So of course, this is not always the case, otherwise I won't be here. So let's look at the scenario where we want consensus. We want everybody to join in. In this case, first, we show that it's not, the equilibrium we saw earlier is no longer in equilibrium. Why is it no longer in equilibrium? Because think about it. If I receive the low signal, what does it mean? It means that the product will only be manufactured if the 2 other colleagues receive the high signal. Now, if I know that the only way I will get charged is if there are 2 positive signals. I would also want the product at some probability, which is what we call the social insurance of the crowdfunding. And in equilibrium, these 2 forces will balance each other, because if low, and here, yes, I said it. So here the equilibrium is one where a low type player assigns almost 30% probability of joining in, which decreases the correctness, the probability that the campaign will choose correctly. We call it, so people actually are free riding on the signals of others, and in equilibrium, these 2 forces are balanced. So we saw 2 schemes, one where we have one where we have b equals 1 and b equals 3. We wanted to compare these 2 schemes. We wanted to ask which one of them is better. So first we want to talk about, when talking about better, I first need to define what is better. What does better mean? So remember what the crowdfunding was made for, either fundraising or gouging market demand. So we introduce 2 indexes to make sure which is which. And it's the same intuition as in auctions, where you have social welfare or revenue maximization. So here we have social welfare and market penetration. Social welfare is the fact that it's what is the probability that a good product will be manufactured or a bad product be rejected. Market penetration, it's how much revenue. And again, this is a very simplified model. We wanted to keep it as simple as possible. So there are no prices, but you can think about it as the number of contributors, the participation rate, sort of. And so we wanted to see what is the average number of people who decided to contribute to the campaign, given that the campaign actually succeeded. So first, let's look at the social perspective. We introduced the correctness index, which is basically the probability that the state of the world is good, times the probability that the product succeeded, and when it's low, that it failed. Let's look at it at both of our examples. So again, here, we assume that there is a half probability. When b equals 1, there is a probability of half that the state of the world is good. There is a probability of 0.25, 1 minus p to the third, that all players receive a low signal despite the fact that the world is good. And this is the only case the product will, and this is the only place the product will not be manufactured. 1 minus this gives us the correct probability. And the probability that the product will not be manufactured if the state of the world is L is simply the probability that there will be 3 low signals, which is 0.7. When b equals 3, again, we have this equilibrium. And I will not go over the math. So we can see that a high threshold, in this case, the high threshold yields better correctness, is more correct than the low threshold. So obviously, it's very nice for n equals 3. Our next intuition is to see how well can we generalize this result beyond this very simple example I'm showing you. And the way we chose to do it is we chose to look at what happened to a crowdfunding game when the number of players increases. When the number of players increases is very, very large, n goes to infinity. And we are looking at the threshold which yields the best possible correctness. Now, if this threshold, if this expression, if a theta bar goes to 1, this means the campaign, at least on average, the crowdfunding scheme is very, very good. What do you think? How many people here think it will go to 1? Again, if it would go to 1 and be trivial, I would probably not standing on this stage. It does not go to 1. In fact, no matter what threshold is chosen, this is the best you can do. 1 minus half this quarter, in this fraction. Now notice that it is bounded away of 1 and it increases in p, which means that if the people have good intuition on the product, the correctness will be better. Which is not very surprising, but I'm saying this because later when we talk about penetration, we'll see something else. So the fact that it bounded away from one, meaning that if you want to invest in a very cool crowdfunding project that you are not sure about, I would recommend to do a thorough checkup. Okay. So next we are talking about market efficiency. If I'm now a startup entrepreneur and I want to be able to show my investor that an amazing success in crowdfunding, I less care at this stage if the product is good or bad. I just want to be able to attract as many people as possible, or as much money as possible. It's more true in the real world. But in my model, it translates to this. So we call it the market penetration index, name about to be changed, I think. It's not a very good name, but I'm open to suggestions if maybe participation index, which is basically the expected number of people who will join in, provided that this product will be manufactured. If we cross B, what is the proportion of individuals who contribute to the campaign? Whoa, I have results to show. Anyway, so in the market penetration game, it will be online if you want to check my math. When B equals 1, the probability is half. And when B equals 3, the probability is 1/3, which means if I have 3 players in this setting and I want to be able to attract as much as possible, I should keep the threshold low. Again, let's make sure and see how well does this extend to the general case. So the same definition, the B n goes to infinity, the best B possible, what is the revenue I can extract? So turns out it's 1 over 2 P's, which is the only thing I can say is that it decreases in P. What does it tell us that it decreases in P? When people are unsure about my campaign, about the quality of the product, the entrepreneur can utilize this method to attract more premium for, when people are more confused, they are more likely to lean on the social insurance. Therefore, the total revenue, the participation index will be higher. Now, of course, everybody can see from this table that the next, I'm answering the first question, which is, but n goes to infinity is a very bad assumption. So we examined some calculations for finite sample size, and you can see that even when you have as low as 10 or 100 individuals, then the strategy and the correctness and the participation are usually very close, are about 10% far from the asymptotic number, which we'd expect to see. So our results also give intuition into the finite sample calculations. And finally, because my time is up, I will show the results for a game with a general prior, and I will just show them. And we can see that they hold also when you take mu to be whatever you want between 0 and 1. The correctness is bounded is mu, and the revenue decreases with P. So this was the crowdfunding game. I have a thank you slide like everybody. Thank you.
Time for a couple of questions.
Yes.
So did you try to test some of these predictions versus like data from like real crowdfunding auctions?
So we didn't. This is theoretical work. We didn't go to data, but I can. There is a survey that states that about 8% of all crowdfunding campaigns never deliver, and no, sorry, 20% are disappointing, and out of these 20%, about 10% never deliver. So there is room to and.
Another issue that, I mean, there's the sequential nature that seems pretty important in crowdfunding, but there's also, in terms even for a simultaneous youth game, I can always buy, if it's producing a product, I can buy it, after it's gotten funded by the investors.
So the second part, the second question is, I mean, so in this case, the crowdfunding the entrepreneur can simply give some sort of discount beforehand, so you still have some excess value from joining the crowdfunding, but it's definitely one of the things we intend to go. Another interesting direction, which I skipped over the last slide, so I will just enter it through the back door now, is that basically you have also the congestion effect. I mean, for example, if the crowdfunding goes well, then people might want to join in or use this model to study ICOs and stuff like this. This is also a very interesting direction we are now pursuing.
I have one question. So there is one paper by Economic Jubricas which put some refund bonus aside in crowdfunding activity. Like if you cannot collect the required this B, then you actually give back more money to the agents who contributed. So how that will fit in this model?
So I think if I'm referring to the same article, then I'm talking about some moral hazard issue. A moral hazard issue, for example, so that the entrepreneur can. Here I'm disregarding the incentives of the entrepreneur altogether. He's in the background. I'm saying that he wants to do good, he's just not sure what the quality of his product is. So if you get, it could be an interesting direction. Thank you. It could be an interesting way to see if you can balance the utility. Okay.
So let's thank the speaker. So next talk is Sequential Deliberation for Social Choice by Brandon.
Okay, hi everyone, thank you for being here. So I'm Brandon, the first one here, and my co-authors on this paper are Ashish, Goel, Kamesh, Munagala, and Sukolsak, Sakshuwong. And Ashish and Sukolsak are both at Stanford, and Kamesh is with me at Duke University. So I'm here to talk to you about social choice, and I have sort of three priorities, sort of lexicographically ordered, and if at any point I'm talking about something and you would like to interject and ask a question about something higher in the preference ordering for these things, please do so. That's okay. So the first thing that I want to do is I want to get across to you that social choice is still an interesting question, despite all of the famous impossibility results that you all know. And in particular, computational social choice is a very interesting problem. So if we think about it as a computer scientist. The second thing is that I'll try to give you some sense of my results and the intuition behind why you can accomplish better social choice mechanisms if you use certain kinds of information that aren't just ordinal rankings, but not some sort of full information about the setting. And then the final thing is, if I have time, I'll try to give you some sense of how we prove anything, but that's sort of the lowest thing on the priority list. Okay? So we're talking about social choice, and the classic setting, and I have to put up the example, and I'm very sorry because at this point I'm sick of this example, to be honest, but these slides are a few months old now, and I wasn't as sick of it then. So the classic setting for social choice is voting over candidates. So here's an example of that. These are three of the Republican primary candidates in the United States presidential election who are running against each other sort of late in the race. These were the three. And the classic question of social choice is who should win, right? So we're told there are some number of candidates and there's a population of voters. Each voter tells me I like this candidate better than this candidate, better than this candidate, right? And now we have to aggregate this information and decide on the outcome of the social choice procedure, which is to say, who wins the election, all right? And in a small example like this, maybe we can debate, but you probably think I should use one of 2 or 3 classic voting procedures you've heard of. Maybe I run plurality, in which case Donald Trump won. Of course, in the United States, we did run plurality, and Donald Trump did win, okay? But maybe in a setting like this with 3 candidates, you think, okay, I have a little bit of choice, but not that much choice, right? I mean, which voting mechanism I use, can it really matter that much? I know that if there are 2 candidates, it doesn't matter at all, right? Everything is majority. So this was not actually the initial picture in the United States primary election. This was the initial picture I think there were like 16 people here, like 16 possible candidates that you could vote over. So the picture was substantially more complicated than just 2 or 3 people. And in fact, it's sufficiently complicated that it's not clear, even in this very real-world example, in the classic setting of voting, whether if I had asked all of the voters to give me a full ordinal ranking over the candidates, whether they could actually have done it. It's maybe not clear. Okay? And this is the classic model for social choice theory, is that we take ordinal rankings over the candidates. But this even is not really the setting I'm interested in. Okay? So I'm really interested in the allocation of public goods, and in particular, I'm interested in sort of problems that relate to public projects. And so this is the setting that I have in mind. I'm curious about voting over the space of what roads could we build, what schools could we build, what parks could we renovate, what bus routes could we fund, things of this nature. And all of a sudden, when you're voting over spaces like this, it is entirely unclear how you would run a classic voting mechanism. Okay? And so at a high level, this is the kind of problem that I'm interested in. Because I'm a computer scientist, I want to be able to talk about it in terms of numbers instead of this abstract concept or something. So let me give you a model for what these possible outcomes are. Okay, so I'm going to make a metric assumption, which is to say, I'm going to assume all the possible things we can vote over, all of these possible outcomes of the social choice, are points in some metric space. Okay, pick your favorite metric space. So in this example, right, we have these 3 candidates, each of them has some location, and then we're going to assume that every voter who comes has some bliss point, I'll call it, which is their favorite possible candidate within this metric space, right? And let's assume that that's a feasible outcome, that you in fact, you could pick whatever their favorite thing is, okay? That's sort of a nuance we can talk about offline if you want. And finally, if you're wondering why a metric, think of the triangle inequality as being a rationality assumption. Right? What does the triangle inequality say for a social choice problem? It says, okay, if there's some objective sense, not a particular one, but some objective sense, in which Donald Trump and Ted Cruz are closer to each other than they are to John Kasich here, then it should be the case that if you like Trump much more than you like Kasich, you should like Cruz much better than you like Kasich. Okay? This is the kind of rationality assumption that a metric or a triangle inequality will give you for social choice, and we're going to assume that. So that's the model for where the possible outcomes lie. Now, what's the objective? What do we want to try to accomplish? So we're going to work, broadly speaking, there's some nuance here, in the implicit utilitarian framework. What is that, if you haven't heard of it? The objective should be obvious. We're going to want to maximize the social welfare, the utilitarian social welfare, right? And this is just written in terms of everything being located with bliss points in some metric space. The utilitarian social welfare will just be that we want to minimize the sum over all of the voters or over all of the agents of the distance from their bliss point to whatever outcome that we choose. So we want to choose something that's close to the bliss points of the majority of the agents, right? That's the idea. Yeah, Kira?
So the model is that there's one metric space that's common between everyone and a person's preferences is characterized with the
Correct. Yes. So there's some objective sense in which candidates are close to each other. Yeah, yeah. Okay, and obviously we want to minimize the social cost, right? So this is sort of a negative of the utilitarian social welfare in some sense. I should also say the distortion is this quantity that people look at in implicit utilitarian sort of world. So we want to minimize the social cost. I'm going to give you some rule for determining the outcome, and then I'm going to measure the quality of my outcome based on the distortion. Here I've written this just sort of as an approximation factor, if you're more familiar with the approximation world. I should point out a couple of related works in the implicit utilitarian world. I'm not going to go over all of them. I think that would take us too far afield. The first I should definitely mention, because I think Ariel Prakasha is right here, who introduced this model in 2006. And there you should think of the distortion as a slightly different quantity than this. There you should think of, I really do have a full ordinal ranking over the outcomes. And the distortion is this interesting quantity. It's what is the worst case over all cardinal realizations that could have produced my ordinal ranking of the approximation that I get under my mechanism, right? So that was introducing it. There have been many other works. The thing that's probably closest to this work is a recent paper I would highly recommend by Angelevich and Postel. So they're working also in this model where you have this metric assumption, and they're also looking at randomized social choice mechanisms, which is similar to what we're doing. They study slightly different spaces and give slightly different guarantees, and I don't want to get into the nuances of that right now. Okay? All right. The thing that they end up finding for general metric spaces that is sort of the best known mechanism that you could give if you have this metric assumption and you're allowed to use randomized rules, and what you want to do is to minimize this social cost and expectation, which is this distortion quantity I've just given you, is a very simple algorithm. And it's called random dictatorship. You may have heard of it. So here's the whole description of the algorithm. If we were to perform some social choice, so we're going to decide on, say, who's going to be the president of wine next year, I'm going to run a lottery and pick one of you uniformly at random and ask you to just tell me who it is. Okay? You can decide whatever you want. That's random dictatorship in a nutshell. It's just this uniform lottery. And this is almost folklore. This is very easy to see, and I'll show it to you in just a second, but I don't know that it's particularly attributed to anyone in specific, which is that the distortion for random dictatorship is at most 2, or you can think of this as the approximation factor, the way that I've talked about distortion, is at most 2 for general metric spaces, and this is tight not for any mechanism, this is tight for random dictatorship. It achieves this on specific examples. And I'll show you both of these right now. The proof is like, I think 3 lines, but it could have been shorter even. The basic idea, just write the expected social cost of random dictatorship, apply the triangle inequality once. So I'm going to choose some agent, right? And I'm going to look at the distance of the outcome of this random draw to the optimal points. Just write the triangle inequality through that agent's bliss point that you drew. You split this up into these 2 things, and then you sum out, and you get exactly twice times the optimal social cost. It's trivial. And the lower bound is also trivial. It's just a star graph. So think of there being a metric space where every agent is the leaf on some star, and there's some central vertex which has distance 1 from every agent, and every agent has distance 2 to another one of the leaves, another one of the leaf agents, right? Random dictatorship, of course, will always choose a leaf, right? But of course, the optimal thing to do is to choose the center, and as the number of agents goes to infinity, this gives you the lower bound of 2, and this is sort of trivial. What's interesting about this is this should provide you some intuition about how you could do better than random dictatorship. Despite the fact that maybe it's the best thing we know, I should point out it's not the best thing provably in general metric spaces. It's just the best we know, and that's maybe the most interesting open problem in this area. But it seems kind of silly because it seems like the example that it's failing on is the simplest possible example, and it's the one where we should be able to do well. It's the one where there's an excellent compromise solution for all agents, right? So that's the first insight that we have in our paper, that we want to define mechanisms that beat random dictatorship in some space. How should we do this? Intuitively, from what I just said, we should be trying to find compromise solutions, okay? And the stars is that example where we want to do this. And this is the main takeaway intuitively. There's a second intuition, which is a little bit more subtle, which is that we should be iterating on the solution as well. That is to say, we should be iteratively compromising, potentially. And if you want to think about it in a picture, think of something like a tree here, where all of the agents are at the bottom. These are feasible outcomes, but no agents have bliss points there. And then you want to choose the root of some big tree. Okay? I could ask agents, force agents somehow to compromise, and I really want to keep iterating and going back up the tree and forcing them to compromise more and more and more. I want the global compromise solution more than I want local compromise solutions. Making both of these insights formal and giving an algorithm and proving something about it at a high level is what we're about and what we're trying to do. And the way that we force agents to compromise is to consider one of the most classic problems in economics and game theory, which is the bargaining problem, right? You may have been wondering, I keep saying we're going to force the agents to compromise. How are we going to do this? The bargaining problem supposes that we have some 2 agents, and they have some preferences. Preferences are usually defined over some convex space, but let me just bring back this example. We tell them, okay, you 2 have to come to some consensus and tell us what you want to be the outcome. If you can't come to a consensus, then some default that I've chosen will be the outcome, right? What's the intuition behind this kind of a thing for forcing compromise? The idea is maybe they disagree about their top preferences. So if you told them, okay, come up with a consensus outcome, they just bicker indefinitely right, over whether Kasich or Cruz should be elected. But now if I tell them, okay, in 5 minutes, if you haven't come to a conclusion, then we're going to choose your least favorite outcome for both of you, that should provide some incentives to get the wheels moving, right? That's the idea. That's the intuition of how we're going to use bargaining. Thank you. In fact, actually, in an interesting note, if you know one of my co-authors, Ashish Goel, he says this works with his children sometime when they're deciding where to go to eat for dinner. So if you need a helpful hint, the bargaining problem might be helpful in your life. Okay. So the classic work on this is from John Nash, a long time ago, which is to say that if you have certain axioms on what an agent should behave like in a bargaining situation, certain rationality assumptions, then the solution to the bargaining outcome, that the normative solution, the outcome they should choose, if they're rational, is the one that maximizes the Nash product. For those of you who are familiar with the resource allocation world and problems like this quantity should look very familiar. This is sort of the two-player version of the Nash social welfare, more or less. It's the same basic idea. So if I think of the normalizations as being 0 here, that is to say that I have 0 utility for this default alternative that I've defined, this will just maximize the product of utilities. Because I've written everything here in terms of costs instead of utilities, this will maximize the distances in the minus here rather than the other way around. So you want to minimize sort of this product, is the idea. Okay? And this is subject to individual rationality, of course. Okay, so this is our model for how we're going to force agents to compromise. We're going to force them to play a bargaining game. And we're going to assume that the outcome of the bargaining game will be this Nash product maximizer. Right? Just say, if this is true, what will happen and what kind of an algorithm can we design? If you don't like that descriptive assumption, if you're an empiricist or something like that, then just allow me to play here for a moment and think of this as a black box that I can query. Okay, that's a different way that you could think about it. So sequential deliberation is the algorithm that we define for social choice in these kinds of settings. Remember that it's got to work even if we have massive outcome spaces. And I'm not allowed to sort of get these massive ordinal rankings over all of the agents. Instead, I'm going to start with some agent chosen uniformly at random. This is exactly what random dictatorship does. And I ask her, what's your favorite outcome? Okay? Now we're going to start iterating for some number of time steps. And what we're going to do is draw 2 agents independently, uniformly at random from our population. Okay? And we tell them, you two have to bargain, and the default alternative is this previous agent's bliss point. So if you can't come to any consensus and tell us what you both prefer, then that's going to be the outcome. All right? Now, just after you've done this, update what your current bliss point is, your current outcome is. And just iterate on this, and after you've gone through this loop some number of times, output whatever your final thing was. Right? So it's just this, we're just sequentially forcing agents to bargain and updating the default alternative based on what happened in the previous round. And we're therefore defining this Markov chain. And at the end, we're just going to output the last thing, which is going to be like the expectation out of this Markov chain. Is the algorithm clear? Okay. So I think just going to have time to describe the results, and I'm not going to get into much of the technical details of the proof, unfortunately. Happy to talk about it offline. So this is what we find. For general metrics, any metric, right, the algorithm that I just described will give you an upper bound of 3 on this sort of approximation to the optimal social cost, this distortion quantity, which is, of course, not actually as good as that bound I just gave you for random dictatorship. Not quite. It's close. I would actually point out this is at least as good as any deterministic mechanism, which is interesting. That's from different work by Anshevich. But actually, general metrics can be very strange. And so what we do in this paper technically is reduce the range that we're looking at from these general metric spaces to something a lot nicer called a median graph. Median graphs are nice in a social choice setting because if agents have bliss points that lie on median graphs, then what you're guaranteed is to have a Condorcet winner. So you can think of median, and in fact median graphs are sort of the largest such metric structured space for which that's always true. So you can think of them as being sort of the largest, very nice space for social choice under this kind of metric world. Okay? They include graphs like grid graphs. They include all trees. And in particular, they include hypercubes. And hypercubes are actually somewhat canonical for this class, and they play a large role in our proofs. And for median graphs, you can show that this actually gives you a very close to optimal solution. Okay? And it gives you a very close to optimal solution without me having to elicit tons of information from all of the agents. Right? It's a very simple mechanism to describe. Right? And it beats random dictatorship rather dramatically in this space. Okay? And so that's the key result, the main result. There are a few other things. We give a series of lower bounds, and these are kind of interesting. So these tell you how well you can do with certain kinds of information. In particular, if all you have is pairwise local information, you can't get optimal. That's sort of surprising and interesting. This is even for median graphs. So even on median graphs, if all I restrict you to is you're only allowed to choose choices that are pairwise Pareto efficient, that is to say they're on some shortest path between two agents, the only reasonable things I could expect two agents to ever tell me, then you can't get optimal. You're still bounded away, and we get quite close to this. So I think that's the most interesting lower bound. We also give a whole list of properties that I would love to talk to you about offline. There are a lot of other good reasons why I think this is a good mechanism beyond just this basic distortion bound. Okay? And I'm going to skip the technical details now and just mention that the biggest open problem that I mentioned earlier is still that in this space, it's not clear that random dictatorship is actually optimal for general metrics. It's a very interesting open problem. So now I'll just skip through this stuff. Thank my co-authors again and ask any questions. Yeah.
Any question?
Very interesting. I guess one thought I had was, would it be fair to say that some of the information recitation is hidden away in the bargaining step?
Yes. Yes, they would absolutely be fair. Yeah, so there are two ways you can think about this, right? So it's a good question. So I was mentioning, note that the whole point of implicit utilitarian social choice is that I'm not told all the numbers. I mean, if you told me the whole metric space, this would be kind of trivial, right? And so what I have to do is try to pick something only knowing this ordinal information. But of course, in order to bargain and maximize that Nash product, the agents have to know something about the metric space, right? Totally reasonable. So one way you can think of it is that this is kind of implicit utilitarian, but not completely. It is in the sense that the mediator never has to ask for numbers. The agents never have to sort of report 9.73, they never have to give you a meaningful scale, none of those kinds of things. It is not in the sense that agents have to be able to reason about their quantitative preferences. So yeah, I totally agree in that sense. And if you want, you can think of that as being the kind of normative content, as being, okay, well, yes, if agents at least can reason about their quantitative preferences, even if they can't give you very specific numbers or something, we can do better. Or you can think about this as an algorithmic black box if you prefer that. Yeah.
So you're maximizing utilitarian social welfare here. You could alternatively maximize a weighted sum of agents' utilities, which is equivalent to, if you do this for all different weight vectors, mapping out the Pareto frontier of the solution.
Yeah.
And it's clear how to do that for random serial dictatorship. I'm wondering if in your mechanism, the Nash bargaining solution, I guess maybe you could give more bargaining power to one party and do a similar thing such that you can map out the entire Pareto frontier.
Give more bargaining power to one agent. Yeah, maybe. It's possible. I'm not sure how you would have to do that. You'd have to modify the actual bargaining black box somehow and then recharacterize what the normative solution should be. This seems possible, yeah. But I don't have a deep answer about it.
Do you know the speed of mixing? So you analyze something about the...
Yeah, of course. So so this is a Markov chain. So that number I gave you, 1.208, that's the stationary expectation. But actually one of the nice things about the analysis is that you actually are getting uniform convergence over the marginals on a hypercube, and it's exponentially fast. So you get to I think 1.22 within 9 steps. It's extremely rapid. So the tight results, almost tight, the very close to tight results, almost optimal, are for median graphs, which are a restriction that include things like grid graphs and trees and hypercubes. The property itself is actually slightly tricky to define, so I can maybe do that later if you want. We get an upper bound of 3 for general metric spaces for our algorithm, which is not as good as a random dictatorship for general metrics, but is actually at least as good as any deterministic mechanism in this space would do.
So how do you decide on the number of round of deliberations in your algorithm? And does that have any effect on the distortion?
Yeah, so this is sort of a very monotone thing. So if all you care about is the expected distortion, run it for as many steps as you're willing to run it for. Right? So it's not the case that you run it for 9 steps and then you have to wonder to yourself, okay, should I stop now or should I keep going if I have more time? Right? I mean, if you keep running it, it only gets better. But so this is related to the question about the mixing time and whatnot that we can bound. You get very close to our guarantees if you run it for like 10 steps. So you should think of needing to run this for a small constant number of steps. This has interesting implications also if you're worried about sample complexity. So actually, we can get these kind of expectation results even if it's a population of 1 million voters, even if I only actually bring, say, 30 of them uniformly at random into a room, which is kind of interesting.
Nice.
Yeah. Let's thank the speaker. The next talk is The Strategy of Experts for Repeated Prediction by Amir.
The pointer. Oh, yes. Okay. This works. All right. Yeah. I think you can hear me. Okay. This is work. Strategy of experts for repeated predictions. Basically, this is an investigation of how an expert can maximize his impact on an audience. And thanks to my co-authors, Yossi, Azar, and Yishay, Mansour, both of Tel Aviv University. And instead of all those generalities, let's jump into a very representative specific example. And I'll ask you to consider a futures market. If you don't know what it is, then it's a market where traders buy and sell an asset that will be delivered and paid for at some known future date. And in effect, this is a prediction market for the true value, because if you know the true value better, you can sell for less or buy for. You can sell for more or buy for less, of course. And the current price in the market represents some sort of consensus prediction. That's actually what markets do. Okay, now let's go on and consider an expert in that market. The expert is reputed, is assumed to have a more accurate signal than regular traders, but we don't assume that the trader is. The expert is not a trader himself. Actually, predicting is what he does. And his profession is based on his reputation for accuracy, and that's why he wants to make a good impact. There are several kinds of people who match that label, but that doesn't concern us here. And what does an expert do? We said he does not trade, so he contributes by making a public prediction. He utters, this is my prediction, and this is public. Everybody hears it, and A, gets influenced by it, and B, in retrospect, can check the accuracy of the prediction, because remember, there's a date in which the truth will be known. Now, the compensation of the expert is greater. It goes up with how much he contributes to predictions value to the market. Get more specific about that later. And, okay, that was specific scenario for this question, but of course there are several other many other scenarios where this applies. It applies everywhere where the public is interested in some continuous variable that will be known at some known future date. For example, the weather or the climate is obvious. Election result, that's been discussed, previous talk. Sports gambling, that's extremely common, a huge industry. And there's lots of gambling and prediction about movie box office, book sales, etc. I'm sure that the pundits have been discussing the expected movie box office take of the latest Star Wars film for, say, like the last 2 years, and I've been updating their forecast in the past few weeks. So there's a lot of et ceteras here. Scenarios that we are considering is that the expert has no obligation to speak at any given time or at all. Okay, one scenario is that the expert may speak at most once at a time of his choosing. There's time between now and the event, and the expert all the time knows more than the market, but he needs to choose when to make a prediction. That's the last time he may make such a choice. That we have done for last year's EC, and that's been in this. The other variation is that the expert may make multiple predictions, meaning that he can, at times that he's allowed, may revise his previous prediction and say, okay, my revised prediction is this and that, and make multiple serial predictions, and this is the topic of this talk. Okay, let's talk about what an expert is. We attribute a number called an expert quality to the expert. The expert knows things that regular traders do not. That's what's supposed to make him a trader. We don't necessarily assume that his expertise is real. Actually, it's enough that he has a reputation for being accurate. It doesn't really matter if it's really accurate, because this is a one-shot game that we are considering here. And what we assume here is he gets a private signal, y sub t, at every integral time t. So he gets a private signal. There's an expert quality number between 0 and 1 that measures what part of the market uncertainty the expert knows, meaning that his uncertainty is only 1 minus q of the general market's uncertainty. And that's also important. The quality of the expert is common knowledge. Everybody knows it, including himself, of course. Okay, well, what's really the dilemma here? Okay, suppose the expert is allowed to predict at given periods, T1 to Tn, all of them before the time that the truth is known. At every such period, he may make a prediction, but he's not forced to, and he gets scored by a scoring rule, by a proper scoring rule, at each individual prediction, and all those scores are added up, and the aggregate is his compensation. So the question is, when is the right time for the expert to make his first prediction? And when is the right time for the expert to revise a prediction that he's already made? And second question that is intriguing is, should the expert tell the market the truth? Okay, I'm going, okay, we have said we are going to compensate him by a proper scoring rule. Now, proper scoring rule motivate telling the truth in the last prediction, but not necessarily in any other prediction, in any but the last prediction. Okay, I'm going to spend some of my precious time by trying to convince you that it's not always right for the expert to tell the truth, or that it's sometimes proper to hide or tell lies. For example, public wants to predict a variable's outcome will turn out to be X. This is something that will be revealed. And they get signals of that outcome, and every signal of that outcome is X plus epsilon, is IIDs every time a fresh X plus epsilon with probability half, and X minus epsilon with probability half. And of course, both X and epsilon are unknown. So if you see one signal, doesn't tell you very, tells you very, and doesn't tell you much. Okay, the schedule of getting signal is on Sunday, the expert gets a signal. On Monday, the public gets a signal. On Tuesday, the expert gets another signal. And on Wednesday, the outcome X is revealed. Now, question, should the expert reveal his information truthfully on Sunday? What do you say? I say no. Why? Okay, the structure here is whoever sees two different truthful signals is able to calculate the outcome exactly, right? It's simply the average. If they are different, then we know the outcome exactly. So, by not speaking on Sunday, the expert prevents the 50% probability that the market will know X on Monday, and still preserves a 75% probability that the expert can announce X on Tuesday. How? By seeing two different signals. There's 75% probability of this happening. So the expert should not reveal his prediction on Sunday. He can do even better than concealing the truth is lying about it. Because if he's going to lie about his signal, the market is certainly going to see two different signals, going to go into a wrong conclusion, and then on Tuesday the expert will tell the truth, and the market will be misled. But even hiding is good enough. Okay. Okay. So let's before discussing this, let's summarize what are results here. And the optimal prediction policy, the expert does the following. Okay. Despite what I've shown you in the previous slide at some length, the optimal policy in this scenario is to always tell the truth. That's optimal for the expert. And to make a new prediction whenever the expert has a fresh signal. Okay, so the policy is very simple. Tell the truth and speak whenever you're allowed to. That's speak all the time. Don't hide information and do not lie. That's in the multiple prediction scenario. And asymptotically, the expectation of the expert is to be rewarded. This is not, actually it's wrong. Rewarded something that is proportional to log of the time left and proportional to his quality by the logarithmic market scoring rule mechanism. Okay, just to mention the previous work, the single prediction result, just to contrast it with the previous result, there the result was the optimal policy was threshold based of predicting when the difference between the market price and the public price and the the market signal and the expert signal differ by something that is bigger than a threshold, which is more or less square root of 2q log t. And expectation of the expert in that scenario was approximately q log t from optimal policy. So this screws from log t to log t, just by allowing multiple prediction. In this case, of course, since it's a single prediction, truthfulness is not an issue, because in the single prediction, the proper scoring rule is motivation enough, good enough to tell the truth. Okay, how does it work out? Let's look at the market as a random walk. Of course, this is a very old hypothesis in economics that according to the random walk hypothesis, market prices evolve according to a random walk and therefore cannot be predicted. We use a reverse time notation. Let's mark the true value that will be known time 0 as x sub 0. And with t periods remain the market prediction x sub t. So we use, time goes backwards. This is random walks going back from period 20 to 0. That's how the market is going to evolve. And okay, a random walk may be written as that the true price is a random walk away from the current one. But we can just switch sides and equivalently say that the current price is a random walk reversed in time from the true value. These are random walks are time direction neutral. So we can say that. And there's a common assumption in economics that random walks of markets evolve are distribute normally or log normally, which is the same if you take logs of stock prices. Then we are talking here about a Gaussian random walk or a log normal Gaussian walk. We are going to assume that it is a Gaussian random walk. We can do that without loss of generality. That's our assumption. And okay, that's the market's random walk. What does the expert see? We model for the expert. We model the expert as having two random walks. One of them random walks is for the expert's uncertainty. And the others are actually, it's reverse order on the slide. The other is what the expert knows that the market does not know. And that's the difference. That's the difference between the market signal and the expert signal. That's a random walk representing the expert knowledge. And if you add these two, we assume that they are independent. His knowledge and his uncertainty are independent. And summing, we get the market's random walk. Now, for some reason, this does work. Okay, the knowledge is a Gaussian random walk with variance q, and the uncertainty is a Gaussian random walk with variance 1 minus q. And since they are independent, if you sum them, they're going to sum to the they're going to sum to the standard Gaussian random walk with unit variance. Okay, so this again is the market's random walk at 20 periods to end. The value is 109. That doesn't matter a lot. And here we put an example of an expert's random walk. Notice the expert's random walk are going to end in the same point, of course. When the time comes, everybody knows the truth. This is a hypothetical example of an expert who knows everything. He knows the result beforehand. His quality is equal to 1. This is an expert who knows nothing. And since my time is up, the logarithmic scoring rule is the right incentive. Okay, I did not expect, there's a reward expectation. Never mind, conclusions. We analyzed the strategy of an expert who may revise previous prediction. What we found that the logarithmic scoring rule is the right incentive. I didn't really get into, have time for that. You make a prediction whenever you have fresh information. Better experts generally receive larger rewards. That's because the expectation is proportional to Q, to the quality. And that's it.
Any question?
What if it's, say there's a budget on the number of signals you can obtain as an expert?
You buy your signals, yes.
Yeah, and I don't know if I want it to be like a cost or just like you get 10 signals and there's 100 periods. In some sense, having information early lets you make predictions early, which might be valuable, but it also is less, there's some force asking you to take all of your samples towards the end because then you'll have a more accurate.
That's about going halfway between predict only once and predict whenever you want. What you're saying, you choose 10 periods in which to predict, and
Where would they be?
it's a good question. We talked sometimes about analyzing those halfway. We didn't actually get to that. Actually, they are very different domains. The single prediction is threshold based, and the predict whenever you want, as you saw, is talk all the time, don't stop talking. I don't know. I would say it would be something similar to the single prediction case. With some, I would expect some logs in the expression. I would not make any further predictions.
Yeah, let's thank the speaker again. So our next speaker is Dennis. He is going to talk about the price of uncertainty in present bias planning.
Right. This is joint work with Susanne Albers, and it's also the last talk for today, so I try to make it as painless as possible. It's going to be about a model from behavior economics called present bias planning, which tries to explain why people tend to behave inconsistently over time. And the basic idea is that because we all tend to assign disproportionately greater value to the present than to the future, we are prone to suboptimal behavior like procrastination or the abandonment of long-term goals. But for those of you that are not familiar with the model yet, let me just introduce it to you with a little toy example. So assume we have an agent named Alice, and Alice wants to prepare for a run. And she can do so by within 2 weeks with 2 different workouts. So workout A is a very easy workout, and she only has to pay a cost of 1 each week. But as a result, she's not very well prepared for the race, and in the end, she has to pay a cost of 13 to actually run the race. And we can model this scenario with this task graph you see on the right. So the blue path is what happens when Alice does workout plan A, and the first 2 edges are the 2 workouts, and the last edge is the actual race. Her second option is workout plan B, which is a lot harder. So she pays a cost of 3 in the first week and a cost of 9 in the second week, but as a result, she's much better prepared, and for the actual race, she only pays a cost of 1. And then there's one more thing that she actually could do, which is not very smart, but she could still do it, namely to mix between the 2 workouts. So either do workout A in the first and workout B in the second week, or workout B in the first and workout A in the second week. And as a result, she will not be prepared at all and pay a cost of 16 for the final race. So now if Alice would not be present biased, then clearly her best path from S to T is just to do workout B, because that's the cheapest path that she could choose. But Alice is present biased, so she reasons in a different way. And let's assume that Alice is able to see current cost accurately, but she discounts all future cost by some constant factor beta, and we call this her present bias. And for now, let's assume that her present bias is 1/2 plus epsilon. Also, let's assume that there's a reward placed at T to actually motivate her, and this reward, let that be 28 for the moment. Now, in the first week, when she's located at S, she must decide between workout A or workout B. If she chooses workout A, then, well, she sees this cost of 1 accurately, but all the future cost is discounted by beta, and in that case, her best choice is the orange path, which her perceived cost for this path is 8 plus 14 times epsilon. Similarly, if she wants to do workout B, then again, she sees this cost accurately, discounts everything else by beta, and she has a perceived cost of 8 plus 10 times epsilon. So she has a very slight preference for doing the workout B. And furthermore, her reward, because that's also in the future, she discounts that by beta as well. And so her perceived reward is 14 plus 28 times epsilon, which is still large enough to keep her motivated. So this is more than her perceived cost, and therefore Alice will do workout B in the first week, and then she will arrive at this node B, and again the same procedure repeats, but this time something has changed. Now suddenly the blue path, so doing workout plan A is suddenly more attractive to her from the cost, and the reason is because now this plan actually pushes the expensive part to the future. And so Alice sort of procrastinates and prefers this blue path, and it is still less than her perceived cost. So again, she will be motivated to continue to the node BA. But then, right before the race, Alice has a chance to again reevaluate her plan, and now her perceived cost is 16, and this is more than her perceived reward. And at this time, Alice will actually quit. Okay, so this captures all the phenomena that we expect from present biased agents in a nutshell. Okay, so before I continue, let me just give you a quick overview of some related work. So this model that Alice uses to discount her cost, this is based on a very standard model in behavioral economics called quasi-hyperbolic discounting, and it was introduced by Leibson. And then this idea to model an agent's behavior with the help of these task graphs, this was proposed by Kleinberg and Oren, and this more or less forms the basis of all of our work, but it also has sparked a lot of other research. And one paper that's of particular interest to us today is by Grevin et al., where they introduced this notion of a variable present bias that, in contrast to what I've shown you so far, does not stay fixed, but actually can change over time with respect to some probability distribution. And we're going to use this notion at a later point in time, but you will see this in a moment. Now, most of our work so far has concentrated on something that maybe you could call it incentive design. So the idea is to make very slight changes to the setting in which the agent finds herself in the hope to positively influence her behavior. And something that Kleinberg and Oren actually suggested in their work was to prohibit certain actions for the agent, and you can implement this by removing edges from the task graph. But unfortunately, we were able to show that finding such optimal subgraphs is a hard problem, and it's also a hard problem to approximate within any reasonable factor. So earlier this year, we looked at a natural generalization where instead of prohibiting actions, you just assign penalty fees, and you can do this by simply assigning extra cost to the edges of the task graph. And now finding these penalty fees, which we will also call cost configurations, this is still a hard problem, but at least there's a reasonable approximation algorithm for it. So you can compute a two approximation. So what I'm going to show you today is, so far, all of these incentive design problems, they really depended on accurate knowledge of the present bias parameter. But in practice, this is information that we really cannot hope to have. So I guess it should be obvious that it's really hard to find the exact present bias parameter of an agent. And instead, we might only have a vague idea of what range this parameter is in. And so today, I would like to show you how you can design cost configurations that work well with respect to any present bias parameter in this range. Okay. Now, to introduce this to you, let's come back to the model we've already seen. And let's assume that now we're unsure whether beta is 1/2 plus epsilon or 1/2 minus epsilon. So I've already shown you the case with the plus epsilon. Now let's see what happens with minus epsilon. So in this case, Alice will actually have a preference for A in the first week. So she will move up to this node right here. And at this point in time, she has no reason to switch to work out plan B. So she just sticks to A. And as a result, her cost for the final race is 13 instead of 16. And is now, this is actually covered by her perceived reward. So now Alice will successfully complete the race. And whenever an agent does not quit on her path from S to T, we call this motivating, a motivating instance. And our goal is to design cost configurations so that the instance becomes motivating for all potential present bias values. So how could we do this in this scenario? Well, one thing that we could do is, of course, bad things happen whenever Alice takes workout plan A. So we can just assign some extra cost to this edge, and if this cost is large enough, then Alice will just walk along this bottom path down here, which is also her optimal path with respect to the reward that we have to spend to keep her motivated. And so in this case, even though we don't know the exact value of beta, we can actually construct an optimal cost configuration. So that's good news, but the obvious question is, can we always do this? And so in order to quantify the loss that we may occur if we have to design a cost configuration that works for a lot of present bias values at the same time, instead of just one, we introduce this notion of the price of uncertainty. So let B be the set of all the potential present bias parameters, and let RGB be the smallest reward that we need to spend if we want to design a cost configuration that is motivating for every present bias parameter in this set B. And then we can define the cost of uncertainty as just this value RGB divided by so to say, the worst case reward that we have to spend whenever we would know what actual present bias parameter from the set B we're dealing with. Okay, so in the case of Alice's example, this price of uncertainty was 1, but it's possible to construct instances where the price of uncertainty becomes larger than 1. And in our paper, we give an example where it goes to 1.1. But when you try to do this yourself, you will soon notice that it's actually not that easy to come up with these instances. And so the question is there some natural bound on this price of uncertainty? And, well, the good news is there is. And we can do this by just constructing a cost configuration with the desired properties. So let's consider the minimum present bias of our set B. Let this be A. And then what we do is first we need to find the path P from S to T that minimizes the maximum perceived cost along its edges with respect to the present bias parameter A. And now the maximum perceived cost on this path, this will actually give us a lower bound on the reward that we have to spend to keep an agent with present bias A motivated throughout the task graph. All right, and now if the agent would actually travel along this path P, everything would be fine, but of course we cannot really expect the agent to stay on this path, and it might happen that the agent takes some detour P prime, and now we run into trouble whenever the agent takes such a detour, but within this detour, suddenly costs become too high and the agent quits. So one way to avoid this is if we make sure that the cost of the initial edge of this detour is the largest perceived cost that the agent will actually encounter. And we can do this by just, well, taking the largest actual cost in this path P, let this be C, and assign this as extra cost to the initial edge. And this also has the nice property that all the perceived cost at most doubles in this task graph if we do this for every detour. Okay, so we know that for every reward that is A or larger, I mean for every present bias A or larger, a reward of 2 times RGA is going to be motivating. Now, if we put all of this together, then we get a upper bound of 2 on the price of uncertainty. And as a byproduct of this approach, we get a 2 approximation algorithm for this reward RGB. Okay, and this is also, well, at least asymptotically, the best we can hope for in polynomial time, because from earlier work we know that no 1.08 something approximation is possible unless P equals NP. Okay. Now, in the last part of the talk, let me just briefly extend this notion of uncertainty to, well, maybe the next level, in the sense that now, let's assume that the present bias can vary over time. And what we're going to do is we're going to assign a present bias value to all the nodes of the task graph, and then the agent will behave at that node according to the present bias value assigned to it. So let BV be the set of all these assignments of present bias values to the nodes, and then we can define RGBV in the same way as we did for the price of uncertainty. Now, just this time, it's the minimum reward that we need to construct a cost configuration that is motivating with respect to every present bias value assignment at the same time. And then by plugging this into the numerator here, we get the price of variability. And again, we might want to find an upper bound for this, and maybe we try the same approach as before, but now this time we run into a bit of trouble because whenever the agent enters the detour P prime, then, well, maybe the present bias changes while the agent is in this detour. And so to avoid that the agent quits along this detour, we have to raise the cost that we assign to the initial edge, and we have to multiply this cost by a factor tau. So this is a mistake, this should only be tau. Where tau is the ratio between the maximum and the minimum value of the set B. Okay, so we also call tau the range of B. And now the same arguments as before, they give us now a price of uncertainty that is upper bounded by tau plus 1. So in contrast to what we had before, this is actually not constant anymore, unfortunately. So that's bad news. But then on the other hand, it's also possible to construct instances where the price of variability is actually tau half. So again, there's not really much hope to find a much better upper bound or a constant upper bound. So asymptotically, this is more or less the best that we can hope for. And again, also as a byproduct, we get this tau plus 1 approximation for the value RGBV. And now, using results from previous work, we only know that this cannot be approximated within a factor of 1.08 something. So, but this is of course miles away from a constant factor approximation. And this problem actually seems to be a lot harder than in the case of uncertainty. And well, what we were able to show is, using a reduction from vector scheduling, that at least we cannot hope for a polynomial time constant factor approximation unless NP is equal to ZPP. All right. So here's a summary of our results, but I think I ran out of time. So yeah, I'm happy to answer any questions.
Time for a couple of questions. If there are no questions, let's thank speaker again.
Just two announcements. So the cultural program will be starting at 5:45. So now we'll start walking to the venue. The venue happens to be Materials Research Center Auditorium, or MRC Auditorium. It's about 7 to 8 minutes walk from here. Some of the volunteers will be walking. All that you have to do is to follow them. So there'll be some coffee available there. Coffee followed by cultural program. The cultural program should conclude by about 7 or 5 past 7. And then we will have transportation. We'll have a bus and there'll be 3 tempo travelers. So I would request all the registrants who are currently staying in Lee Meridian Hotel